Have you ever really stopped to wonder how computers actually think in just ones and zeros? I mean, it seems like some kind of magic, but it's really just a different way of counting. Today, we're going to decode that fundamental language of computers by exploring the number systems they use. Let's dive in.
Okay, so to kick things off, let's start with something we all think we know like the back of our hand, a number. Say 5,678. We see it, we read it, we use it all the time. But what is it really saying? How is that value even constructed? It's so much more than just a string of digits.
Well, the secret is that it's actually a formula in disguise. What it's really saying is we have 5,000s plus 600s plus 7 tens plus 8 ones. Each number's position gives it a specific value, a weight, based on a power of 10. This single idea right here is the key to unlocking every other number system we're going to look at. And that right there, that brings us to the core concept, the power of position. Honestly, understanding this is everything. It's the hidden engine that makes our everyday decimal system work. And as you're about to see, it's the exact same engine that powers the languages of computers. And this visual here just lays it out so clearly. The 8 is in the ones place, that's 10 to the power of 0. The 7 is in the tens place, or 10 to the power of 1, and so on up the line. Each position has a weight. Remember that word, weight. Seriously, it's the foundation for literally everything else we're about to cover. All right, so we've got our foundation set. Let's do our first translation. We're going to take numbers from these computer languages and convert them back into our familiar base 10 decimal system. Let's see just how that wake concept holds up. Okay, so the native language of any computer, it's binary. It only uses 2 digits, 0 and 1. But, and here's the beautiful part, the rule is exactly the same. Instead of each position being a power of 10, in binary, each position is a power of 2. Same system, just a different base number. Simple as that. And check this out. This table shows it perfectly. Instead of ones, tens, and hundreds, we have the ones place, the twos place, the fours place, the eights place. You get the idea. See that pattern? Each position's weight is just double the one to its right. It's the same logic, just with a different multiplier.
So let's actually put this into practice, right? To convert the binary number 1010.101, all we do is multiply each digit by its positional weight. So we've got 1/8, 1/2, 1/2, and 1/8. Add all of those up, and what do you get? 10.625 in our decimal system. It's really just some simple multiplication and addition.
Now, computers also use a couple of other shorthand languages like hexadecimal, which is base 16, and octal, which is base 8. You've probably seen hexadecimal before, right? It even uses the letters A through F as digits. You see it all the time in web design for color codes. But don't let that fool you. The most important thing to remember is that the underlying system of positional weights is exactly the same.
And just look at this slide, you can see exactly how it plays out. For hexadecimal on the left, the weights are all powers of 16. For octal on the right, they're all powers of 8. The pattern is identical, just a different base. Once you get the system for one, you honestly get it for all of them.
And look, here's it in action. When we apply that exact same multiply and add method, the hex number 1CE8 correctly becomes 7400 in decimal. And the octal number 436.5 becomes 286.625. See, the system just works no matter what the base is. Okay, so we've gone from computer to human. Easy enough. Now let's make that return journey. How do we take one of our decimal numbers and translate it into a language that a computer can actually understand? The method's a little different this time, but it's just as straightforward.
To go the other way, for whole numbers, we're going to need a different tool, repeated division. And all the magic here, it's in the remainders. Let me show you what I mean.
Let's say we want to convert the number 53 to binary. You just keep dividing it by 2 and write down the remainder each time. 53 divided by 2 is 26, with a remainder of 1. Then 26 by 2 is 13, remainder 0. You just keep going. Now, here's the most important part. You cannot forget this. You read the remainders from the bottom up. That gives you the final binary number, 110101.
And don't worry, this exact same process works for any number. It doesn't matter how big it is. Here we see it for 179. And this is a good time to introduce a couple of key terms. That first remainder you get is called the least significant bit, or LSB. And the very last one at the top is the most significant bit, or MSB. Okay, so that takes care of the whole numbers. But what about the stuff after the decimal point, the fractions? Well, think about it. If we use division for integers, it kind of makes sense that for fractions, we'd use the total opposite, repeated multiplication.
Let's walk through this one. To convert 0.625, we start by multiplying it by 2. That gives us 1.25. The integer part, that 1, becomes the first digit of our binary fraction. Then we take what's left, the 0.25, and do it again. Multiply by 2, you get 0.5. The integer part is 0, so that's our next bit. It's just a beautifully logical inverse process, right?
Okay, we've actually covered all the core techniques now. We've gone from other bases to decimal, and from decimal right back again. So let's pull it all together into one complete playbook. Think of it as your personal Rosetta Stone for number systems. Here's the first half of that playbook. This handy guide shows you how to get from binary or octal to other systems. You can see the main methods are substitution, which is a quick way to move between binary, octal, and hex, and summation, which is that multiply and add method we started with.
And here's the other half of the puzzle. This table shows you how to convert from our decimal system into binary, octal, or hexadecimal. And what's the core method? That same repeated division process we just mastered. So between these two tables, you've got the complete guide.
So at this point, you're probably thinking, okay, this is cool, but my calculator can do this in like a millisecond. Why on earth do I need to do this by hand? And you know what? That is a fantastic question, because it's not really about just getting the right answer. The goal is for you to get it, to really fundamentally understand what a number is and how information is structured. Doing it by hand builds that deep, intuitive knowledge that just pressing a button can never give you.
Thanks for watching. See you next time.